In section 4.3, we're going to start looking at finding maxima and minima for functions. In this section, our focus is really going to be on finding absolute extreme points over closed intervals, but we'll start with definitions of absolute extrema or extreme points on any interval and local extreme points. We'll explain how to find the critical points of a function, and we'll define what critical points are over a closed interval. And we'll describe how to use those critical points to find the absolute extrema over a closed interval. So in example 1, let's just look at these graphs. I've written below what the functions are just for reference, but these are just from your book. We're just trying to find the absolute extreme points for each of these functions. So an absolute extreme point is a point that's either higher than or at the same y value as all the other points on the graph. So for the first function, x cubed, on the interval from negative infinity to infinity, what I can see here is that there's no highest point or lowest point. This graph would keep going down to the left and up to the right. So this has no absolute extreme points. But the next function does have a highest value, it looks like at 1 when x is 0. But this function has no lowest value. It appears that this function would keep getting closer and closer and closer to the x-axis, but not ever get there. So this function has an absolute maximum at 0, 1. But no absolute minimum. The next function, f of x equals cosine of x, hits the high point of 1 over and over and over. Also hits the low point of negative 1 over and over and over. And it's totally fine for an absolute extreme point to occur in multiple places. So if 1 is the highest value, even if it occurs infinitely many places, we would still say that's an absolute extreme value. So absolute maximum value would be 1, and it occurs at 0 and 2 pi and 4 pi. So we could say at x equals any integer multiple of 2 pi. So I said 2k pi. Also, this has an absolute minimum value of negative 1. And that happens at pi or negative pi or 3 pi. So at x equals any odd integer multiple of pi. So we could write that as 2k plus 1 times pi, where k is an integer. The next one is a piecewise graph, and it's only defined for x's between 0 and 4. And what we can see here is that there is a highest y value up here at 0, 2, but there's no lowest y value, because when we get down here to negative 2, there's an open point. We don't get to that value, and we can't say what the next highest value is, right? So there's an absolute max at the point 0, 2, but there's no absolute min. Then the next one, we've got an absolute max, the lowest y value at 2, 0, absolute min. And there's also a highest y value up here at 4, 4. That one is higher than all the other y values on the graph. So absolute max at 4, 4. And then the last example here, this graph seems to have a lowest y value at 0, 0 and no highest y value. So this has an absolute min at 0, 0, but no absolute max. So this example was just really trying to get us to look at the graph and see and start to understand what we mean by absolute max and absolute min. What we're going to do later is try to figure out how to find those values without looking at a graph. And so what you want to notice is what you kind of see with the derivatives at these absolute max and min points. So on the second and third example, you can see at the absolute max or absolute min values, the derivative is 0. On the fourth example, the absolute max occurs at an endpoint, and there was no absolute min. But we can see we've got an absolute max occurring at an endpoint, so the derivative there wouldn't even be defined. And let's see, on the fifth example here, we have the absolute min occurring at a place where the derivative is 0, and the absolute max occurring at an endpoint. And then the fifth one, again, we have the absolute min occurring at an endpoint, and there is no absolute max. So we're seeing these absolute extreme points are happening, from these pictures at least, either at places where the derivative is 0 or at an endpoint of the interval. All right, let's look at the next definition. So, this is a formal definition of absolute extrema. So this says, let the function be defined on an interval I containing c. So c is an x value. F has an absolute minimum on that interval at c if the function value at c is less than or equal to the other function values in the interval. And then the absolute maximum would be defined the same way with the inequality going the other direction. But what we notice is that we can include equal to other function values, or the function values at other points. So, like we were just talking about in the previous pictures, the min and max of a function on an interval are called the extreme values or extrema of the function on the interval. They're also called, if they're actually the absolute, then we call them the absolute minimum or absolute maximum on the interval. We're also going to talk about what we mean by local extreme points, and that's the next thing we're going to look at. So just a couple notes. Even though the word absolute occurs in that definition, it has nothing to do with absolute value. These can be positive, negative, or 0, so unrelated to absolute value. And then just like we were seeing as we were talking through those previous examples, one function might have just one absolute, either a maximum or a minimum. They might have both, or they could have neither. So let's move on to local extreme points. We say a function has a local max at a point if there's an open interval containing that point on which the function value at the point is greater than or equal to all the function values in that interval. And again, the local min would be described the same way, with the inequality pointing the other direction. So all we're looking for here is not that the function value be higher than all the other points anywhere on the graph, but just in a region. So the difference here is that we can find an interval around the point such that the point is higher than everything in that little area. So in example 2, we can see that if I just zoom in on this little area, I can see there's a local maximum there, because just in that circle, the point that's on the y-axis is higher than all the other points in that circle, right? So we've got a local maximum here. And similarly, this point at x equals 1 is lower than all the points around it. So that would be a local minimum, even though there are lower points elsewhere on the graph. This point up here when x equals 2 looks like it's both a local max and an absolute max. Because it's higher than the points right in its little area, but it's also higher than all the other points on the graph. So a local max can also be an absolute max. And that seems to be it, right? It appears that this function is falling to the left and to the right, so that should be it for the extreme points. So now let's go look at example 1 again and look at those graphs and talk about the local extreme points for those graphs. So in the first example 1, first picture here, there also seem to be no local extrema. In the second one, we had an absolute max at 0, 1. We also have a local max at 0, 1. And for cosine, all those absolute maximum points were also local maximum points. So I'm just going to say the absolute extrema are also local extrema. The fourth one is more interesting because even though there's an absolute max at 0, 2, there's not a local max there because there are no points to the left of 0, 2. So I can't say that there's an open interval that contains that point on which this point is higher than all the other points in the interval because there's nothing over here to compare with. So there's no local max, and there's also no local min. So to have a local max or a local min, you really need to have a point that looks like a peak or a valley. It can't just be the edge of a peak or a valley. So in the fifth example here, we can see that there would be a local min at 2, 0, but no local max. Because there's no high point that has points defined on either side of it. And then in the last one, we would say there's no local extreme point and either a max or a min. There's neither one. Right, so again, that's just looking at these pictures and trying to get a feel for the definitions. Our next step is to try to figure out, well, how are we going to find these things if we're not looking at a picture of the function? And our tool that we're going to be using is called a critical point. So a definition of a critical point is, let the function be defined at c, and if f prime of c is 0 or f is not differentiable at c, then we say cf of c is a critical point of the function. And something that's true is that if a function has a local extreme point at a value, then f has to have a critical point there. Theorem 4.2 says, if f has a relative min or relative max at c, then cf of c is a critical point of f. So that's just restating what that sentence above said and calling it a theorem. So in example 3 here, let's look at each of these functions that have critical points at cf of c and to talk about whether they also have an extreme point at cf of c. The first one, at cf of c, I can see the derivative is 0 because there's a horizontal tangent line and there is a local max. at CF of C. The next one, there's a sharp turn in the graph, so I can see f prime of C would be undefined, and there's also a local max at CF of C. And in the third one, we have a corner, so another place where the derivative is undefined, and we have a local min at CF of C. But in the fourth one, we have a place where it actually doesn't look like this flattens out, but let's assume that it does. Let's make that sketch a little better. The derivative is 0 at C, but there is no extreme point. Right, so there are no extrema for this graph. So we can have the possibility, even though the derivative is 0, there's not an extreme point. And it's also possible to see this kind of situation where the derivative is undefined because there's a vertical tangent line. Think about the graph of, say, like cube root of x at x equals 0. If there's a vertical tangent line like that, the derivative is undefined, but there's also no extreme point. So if there is going to be a local max or a min, the derivative has to be 0 or undefined, but just because the derivative is 0 or undefined does not mean there will be an extreme point, right? And that's what's highlighted here in this box. So it says these examples highlight the fact that f does not have a relative extreme point at every critical point, right? But if we can know where the critical points are, then we can start using those as where we would search for the extreme points for the function. So we want to get practice with just finding critical numbers, because those critical numbers will be our first step in finding the extreme points for these functions. So in example 4, we just have a few functions, and we're going to be just searching for the critical numbers, which again are the places where f prime of C equals 0 or f prime of C is undefined. So the first one is just the generic quadratic function ax squared plus bx plus c. So what I want to do is find the derivative, and the derivative will be, think about a and b and c as constants that are unknown. So they're just constant multiples when we're thinking about the derivative. So I'll have a times 2x, so I'm going to write that as 2a times x, plus b, plus 0 from the derivative of c. Right? So I want to know, where is the derivative 0? And we'll say the derivative is 0 if and only if 2ax plus b equals 0. And I want to know which x value is it where that occurs. So I would have 2ax equals opposite of b, and x equals opposite of b over 2a. And if you remember the vertex formula, you're thinking, that looks familiar. That's the x coordinate from the vertex formula. And that makes sense, right? Because we know that for a parabola, the derivative is 0 at the vertex, right? And that's just what we are just showing. So the vertex for a parabola, the x-coordinate is opposite of b over 2a. So that's one critical number, and we can see f prime of x is always defined. I can put any x value in, and I can evaluate 2ax plus b. So f prime of x is defined for all x. So the only critical numbers for this function are x equals opposite of b over 2a, or you can write c equals opposite of b over 2a, but it's the x coordinates that we're focusing on here. So just one critical number, and it corresponds to where we know the vertex would be. Next one, find the critical numbers of this function, 9 times the square root of x minus x squared. Here I just want to make note really quickly that the domain for this is only x greater than or equal to 0 because of that square root in the mix. So when I'm looking for critical numbers, I want to make sure they're in the domain of the function. So I find the derivative, and first I'm rewriting this as 9x to the 1/2 minus x squared. So when I do the derivative, I'll have my 9 constant multiple carried along times 1/2 x to the negative 1/2 minus 2x. And I'm going to need to know where this is 0 and where it's undefined, so I'm going to need to clean it up a little bit. So let's see, I've got 9 over 2, and then I'll have a square root of x in the denominator, minus 2x. So we can see the derivative is undefined if x equals 0, but x equals 0 is not in the domain, so that's not a critical number. So now we just really want to know where is this derivative 0. So we'd say f prime of x is 0 if and only if 9 over 2 times the square root of x minus 2x equals 0. And let's see, I would maybe add 2x to both sides. And I want to eliminate the fraction, so I'm going to multiply both sides by 2 times the square root of x. So I'm going to have 9 equals 2x times 2 times the square root of x. And then that's going to give me 9 equals 4 times x to the 3/2. So let's rewrite that as 9/4 equals x to the 3/2. And I want to get to just x. So if I have x to the 3/2 and I want just x, what I need to think of is what's the exponent I would put here so that I get back to x to the 1 on this side. And I remember that if I add another power, I would multiply the exponents. So if I have an exponent of 3/2, I want to raise that to the, not 2/2, 2/3 power, so that I get x to the 1. And if I'm raising one side to the 2/3 power, I better do the same to the other side. So we get x equals 9/4 to the 2/3, or the cube root of 9/4 squared. So there's one critical number. For this function, and it's cube root of 9/4 squared. Let's take a look at this graph, just because this is not a familiar function, and let's kind of see what's going on. So this function was 9 times the square root of x minus x squared. And I'm going to move out here. So it looks like this function goes up and then turns around and then comes back down. I just want to know what this number is, the cube root of 9/4 squared. So I'm going to put it in as 9/4 to the, what did we say, 2/3. So about 1.71, and that looks like exactly where we're seeing this high point. Let's see what the special point is. So special point B was 1.717 and then 8.845. So exactly what we came up with as our critical number, 9/4 to the 2/3. All right. Example C, find the critical numbers of y equals x plus 1 over x. So we would notice the domain for this is x can't be 0, but anything else is fine. For the critical numbers, I want to know what's the derivative, where is it 0, and where is it undefined. So thinking about rewriting the function, I've got x plus x to the negative 1. So for the derivative, I will have 1 minus, because I'm going to bring that negative 1 exponent down, x to the negative 2, which is the same thing as 1 minus 1 over x squared. So I can see f prime at 0 is undefined, but 0 is not a critical number because 0 is not in the domain. Of f. So a critical number for the derivative for the function needs to be in the domain of that function. But we want to know where this derivative is 0. So the derivative will be 0 if and only if 1 minus 1 over x squared is 0. I can add 1 over x squared to both sides. I can multiply both sides by x squared. And then I will see x equals 1 or negative 1. And both of those are in the domain of the function, so both of those are critical numbers. And again, let's just take a quick look at this graph and see. I'll do that in my graphing calculator. Okay, so we had x plus 1 over x. And we can see that it looks believable that we've got critical numbers at 1 and negative 1, where we get these low points on each of the branches. Well, a low point on one branch and a high point on the other. But we can see at each of those places that it looks like the derivative is 0. So it looks like our work was probably accurate. All right, so then the next theorem tells us how to find extreme values, and we're talking about absolute extreme values here. And this applies only to closed bounded intervals. So no intervals where the function values are unbounded, but closed intervals with boundaries. So if f is continuous on that type of interval, a closed bounded interval, so again, closed means it includes its endpoints, then there is a point in that interval at which f has an absolute maximum over the interval, and there's a point at which f has an absolute minimum over the interval. Right, so for closed bounded intervals, we're guaranteed that there is an absolute high point and an absolute low point. Maybe more than one, but we're guaranteed at least one. Right? And those can be found either at critical numbers or at the endpoints of the interval, as we saw when we were looking at our graphs. So our problem-solving strategy is, if we're looking for, it has to be absolute extrema, not just local extrema, on a closed interval, not an open interval. So closed, remember, means including the endpoints. What we're going to do is find the function values at the endpoints as a first step. Find all the critical points in that interval and evaluate the function at those critical points. And then just compare all those function values. The highest has to be the absolute max, and the lowest has to be the absolute min, because the local and absolute, the absolute max and the absolute min have to occur at one of those. They can't occur anywhere else. So anytime the instructions are find the absolute extreme points over a closed interval, we'll go through these steps. And like it says here in this note, it's a little more complicated to find local extreme points, so we'll save that for another section. The rest of this section will be focused on finding absolute extreme points on closed intervals. So here, the first one is a quadratic function, x squared plus 2x minus 4, on the interval from -1 to 1. So our step 1 is compare just what's f of -1 and what's f of 1, and just keep those for reference. F of -1 is -1 squared minus 2 minus 4. So 1 minus 6, -5. F of 1 is 1 plus 2 minus 4. 3 minus 4 equals -1. So far, our highest y value is -1 and our lowest y value is -5. Now we want to know what are the critical points and what are the function values at the critical points. So f prime of x is 2x plus 2, and the derivative is certainly always defined, so it's going to be 0 if 2x plus 2 equals 0, and that would mean 2x is -2, so x equals -1. That happens to be one of the endpoints of our interval. That's fine. We already evaluated that function value, but let's just do it again. So we again note that the function value at the critical number is -5. So we're now at the step of just comparing anything from those lists. And so we would say, step 3, compare function values at endpoints and critical numbers. And so we'll say -5 is the absolute min of our function on the interval from -1 to 1. And what do we come up with? -1 is the absolute max of the function on the interval from -1 to 1. Right? So this is just part of a parabola, and we've figured out that the low point of this parabola is actually what it was, -1, -5. So the vertex is right here, and it continues and hits this point, and we're just looking at this little stretch. So the low point is at the vertex, and then the high point is over here at 1, -1. Again, the parabola itself, if we were considering the whole thing, would not have an absolute max, but on this closed interval from -1 to 1, it does have an absolute max. Next one, h of t equals t over t minus 2, and we're considering the interval from 3 to 5. So first we'll do what are the function values at 3 and 5. H of 3 is 3 over 1, so 3, and h of 5 is 5 over 3, so 5/3. So we have those for comparison. And then step 2 is find the critical numbers. On the interval. If there are critical numbers that are outside this interval, we don't care about them. So h prime of t, we're going to need the quotient rule. So low, not t minus 1, t minus 2 is low. D high is 1, minus high, d low is also 1, divided by low squared. And if we clean that up a little bit, we have the derivative is equal to t minus 2 minus t, so that's just -2, over t minus 2 squared. So we can see h prime is undefined at t equals 2, but that's not in the domain of the original function, and it's also not on our interval, so not a critical number. Because it's not in the domain of h. We can also see that this derivative will never be 0 because there's a negative 2 in the numerator. So we always have something that's non-zero in the numerator, right? So h prime of t is never 0, right? So there are no critical numbers. Not anywhere, not even just not in this interval. There are just no critical numbers for h. But even though there aren't critical numbers, we know there still needs to be an absolute max and an absolute min on this closed interval from 3 to 5. So we would say 3, compare the function values. And the only ones we have to compare are 3 and 5/3 because there was no critical number. So we would say 3 is the absolute max of this function h on the interval from 3 to 5. And 5/3 is the absolute min of this function h on the interval from 3 to 5. The next example, we have x times natural log of x plus 3 on the interval from 0 to 3. Let's just talk about the domain quickly. Domain for this, we need always a positive input for the natural log. So we would need x plus 3 to be greater than 0, which means x has to be greater than negative 3. So this interval is part of the domain, so that's good. So step 1, we'll compare the function values of the endpoints. I'm going to call this f, so we'll say f of 0 would be 0 times natural log of 3, so that's just 0. And then f of 3 is 3 times natural log of 6. And I don't know exactly what that is, but I know that it's positive because I know that natural log of e is 1, so natural log of 6 is going to be bigger than 1. All right, so we've got these two function values on the endpoints taken care of. Our next step is find the critical numbers. And for this, we'll need the derivative, which is going to involve the product rule. So we'll say, okay, the first times the derivative of the second. Remember, when I'm doing the derivative of a natural log of something, I have 1 over that input times the derivative of the input, which would just be 1. And so that's first times the derivative of the second plus second factor times the derivative of the first factor, which would be just 1. So I have f prime of x equals x over x plus 3 plus natural log of x plus 3. So I can see that this would be undefined if x is negative 3, but that's not in the domain of the original function. So there's no place where the derivative is undefined that is going to contribute to the critical numbers. If I want to know where this is 0, this is definitely not something that's familiar to solve. We can't really solve that by hand. So we'd say this is going to be 0 if and only if x over x plus 3 plus natural log of x plus 3 equals 0. And I guess that's probably something I would expect you to you'd be able to have a graphing calculator to look at that. So let's grab a graphing calculator. And let me get rid of some of these. So we want to look at x over x plus 3 plus natural log of x plus 3. There's a way we could kind of reason this out on this interval from 0 to 3, but again, this is not something that I would expect you to be familiar with. So let's let's just take a look at this graph. And we want to look at this graph just on the window, really from 0 to 3. And let's leave it as negative 10 to 10 for the y's. And let's get rid of that one. Okay, so we had x over x plus 3 plus natural log of x plus 3, and we said, okay, let's take a look. So we can see on 0 to 3, this graph does not cross the x-axis. It does cross the x-axis over here at, let's see, around negative, a little left to the left of negative 1, but there's no place where this function is 0 on the interval from 0 to 3. So we looked at a graph and we can see f prime of x is not 0 on the interval from 0 to 3. So we have no extra critical numbers to consider here. So step 3, compare function values. At the endpoints and the critical numbers, and like once again, we only have really function values at the endpoints to worry about here. So we would say 0 is the absolute min of this function on the interval from 0 to 3, and 3 times the natural log of 6 is the absolute max of this function on the interval from 0 to 3. All right, last one, y equals e to the x times cosine x on the interval from 0 to pi. So again, we'll start with function values at the endpoints. F of 0 will be e to the 0 times cosine of 0. E to the 0 is 1, and cosine of 0 is 1, so that's just 1. And f of pi is e to the pi times cosine of pi. I don't know what e to the pi is, but I know that cosine of pi is negative 1. So I could rewrite this as negative e to the pi. So comparing those two, I know at least that 1 is the largest and negative e to the pi is the smallest. And then step 2, we find critical numbers. Let's see if we actually find some on this one. So the derivative would be, again, we'll need a product rule. So I'll have the first factor times the derivative of the second factor. So e to the x times negative sine of x plus the second factor times the derivative of the first, and the derivative of e to the x is just e to the x. And I can see I have an e to the x in both of those, so I'm going to factor it out, and then I'm going to rewrite the other two terms as cosine of x minus sine of x, just so that it looks a little nicer. So there's a cleaned up form of my derivative, and again, the only reason to clean it up is we want to know where it's 0. So if I have it nicely factored like that, knowing where it's 0 will be a little bit easier. So we'd say this derivative is 0 if and only if e to the x times cosine of x minus sine of x is 0. And anything that's factored and equal to 0, we can say, oh, that means either e to the x is 0 or cosine of x minus sine of x is 0. And if we think about the graph of e to the x, that graph is never 0. So this doesn't happen. And cosine of x minus sine of x equals 0, that would mean that cosine and sine are the same value. And we know that that happens in quadrant 1 and in quadrant 3. But we're only interested in the interval from 0 to pi, so quadrant 1 is the place we would like to focus on here, and that's at pi over 4. So finally, we have a critical number to use for our comparison. So we would figure out, well, what's the function value at pi over 4? I know the derivative is 0, but what's the function value? Excuse me, and I'll have e to the pi over 4 times cosine of pi over the 4, excuse me. So e to the pi over 4 times square root of 2 over 2. All right, so then we just need to compare that function value with the other two, 1 and negative e to the pi. I know that e to the pi over 4 is definitely going to be positive, so I know that negative e to the pi is going to be the smallest of these function values. So we can say negative e to the pi is the absolute min of this function on the interval from 0 to pi. And now we just need to know what's the absolute max. Pi over 4 is a little bit less than 1, right? It's like 3/4. So I have like something like 2.7 to the 3/4, and then multiplied with square root of 2 over 2. My gut would tell me that that's going to be bigger than 1, but I would expect you to be able to have at least a scientific calculator to compute that value and compare it with 1. So if I do that, so what did we have? We said e to the pi over 4 times square root of 2 over 2. Yeah, so it's like 1.55. So the absolute max is that value, e to the pi over 4 times square root of 2 over 2 on the interval from 0 to pi. So again, some practice finding critical numbers, and then some practice using that critical number step in the bigger problem of finding absolute extreme values on closed intervals. And we will look at finding local extreme values on open intervals in a later section.